Welcome to the class today. We'll continue the chapter solid state, and today we will do imperfection in solid, that is defective solid. Imperfection or defects in solids. So crystal compounds or crystal possesses a definite orderly arrangement of particles at a definite, or you can say perfect, orderly arrangement of particles at a absolute zero, or you can say 0 Kelvin. So 0 Kelvin or absolute zero temperature is very rare to maintain, and therefore we cannot have a perfect solid. And if the temperature is above 0 Kelvin, when temperature rises, and it has to, because we cannot easily maintain the temperature at 0 Kelvin. So this perfect arrangement, when it is there, then this perfect arrangement which we are thinking at 0 Kelvin, this corresponds, perfect arrangement corresponds to the state of lowest energy of the system. Lowest energy of the system will be there if the perfect arrangement is considered, that is at 0 Kelvin. That you have studied when I was teaching to you the packing, close packing, then I had mentioned these points to you. So when the temperature is elevated, so at a higher temperature, the constituent particles they deviate from their orderly arrangement. They will move from their lattice site, and this deviation will result in a not that fixed pattern, and so your crystal will be imperfect and will said to have defect in it. This deviation of the particles from their orderly arranged places can also be brought about by impurity. So this displacement or disorder is further enhanced due to impurities. So what is imperfection? Imperfection is a displacement of the constituent particles from their orderly arranged lattice site to some other pattern, and so that is your defect. So this defect which is caused here, it changes this imperfection or the defect changes the properties of the substance or the crystal or the compound, and a new property can also, not always, maybe or may not be, can also be added to the compound. So we will do now the type of imperfection or type of defect. So types of defects. There are three kinds. First is electronic, which you have not to do. This is not in your syllabus. Second is atomic. This you have to do. And third is defect due to impurity. This also you have to do. Atomic defect and defect due to impurity, these two. This atomic defect is further divided in two parts. That is your lattice atomic defect and point atomic defect. Then there's you have not to do lattice, you have to do the point atomic defect. Point atomic defect is of two kinds. That is stoichiometric and non-stoichiometric defect. Then stoichiometric defect, two kinds you have to do, is Schottky and Frankel. These two stoichiometric defect you have to do. Then non-stoichiometric, three kinds you have to do. That I will be teaching to you. And similarly, impurity defects also of three kinds you will have to do. So I come to now the atomic defect. So in this flow chart I have told you what are the points we will be covering in this chapter. So atomic defect. Atomic defect is caused due to, number one, missing atom, due to missing atom or maybe atoms. Then displacement of atom or atoms. And the third is presence of an extra atom in a interstitial space or somewhere in the lattice. So this is atomic defect, and then you have studied atomic defect is of two kinds, that is lattice and the point. Lattice you have not to do, point atomic defect you have to do. This defect is due to, number one, imperfect, due to imperfect packing during original crystallization. original crystallization. Students, I am just considering the important point what is mentioned in your reduced syllabus. In your book you will find this is given very huge, much vast. So some important selected point I am writing it here for your convenience. So imperfect packing due to original crystallization, this may be the reason, and thermal vibration, due to thermal vibration at elevated temperature. When temperature is higher, you know, above 0 Kelvin, normally temperature will be there. So because of that, thermal means heat, it will cause vibration in the particles atom, and so defect will be caused. Then this point defect is of two kinds, that is stoichiometric and non-stoichiometric. So we will do now stoichiometric point atomic defect. When defect will not cause any disturbance in the stoichiometry of the compound. No disturbance in the stoichiometry of the compound in a crystal due to impurity or defect, due to defect, not impurity, due to defect. What is the meaning of stoichiometry? This is, you have done, this is the ratio of the constituent particles. Ratio of the constituent particle in their molecular formula. If a compound is having formula say AB2, then in the whole crystal this ratio will be maintained 1:2 between A and B. There may be defects, you will see of various kind, but the ratio of the between the constituent atom will not be disturbed, will not be changed. So stoichiometry will be the same. So now there are two kinds of these stoichiometric defects, that is Schottky. First is Schottky stoichiometric point atomic defect. Schottky defect, very important for examination point of view. This defect is caused when I show you the figure. Say these are the particle 1, 2, 3 and 4. I draw this crystal by showing this particle at some fixed position. So this is method of presentation of a crystal. So this is lattice, that is net of the crystal. These crystals are held, these particles are held together. So this is found in ionic compounds, first thing. So we have a plus sign and a minus sign, a plus sign and minus sign, and then opposite, minus, plus, minus, plus, minus, plus, minus. So this is perfect position. But when Schottky defect is caused, one of the cation will be missing, and from nearby one of the anion will also be missing. Maybe from here, or you can take from here. So this is called vacancy. When a particle is missing from its lattice position, lattice side, leaving it empty, that is called vacancy or the hole. So this is also vacancy. Since your positive ion was supposed to be there, so this is called cationic vacancy and this is called anionic vacancy. So what do you see here? The ratio between positive and negative ion is maintained of 1:1. So stoichiometry is not disturbed. And since here the number of positive ion and the negative ions are same, therefore electrical neutrality, this is another point you have to remember. That is, electrical neutrality is maintained. Electrical neutrality is not disturbed, remains the same. And the positive and the negative ion which are missing and causing vacancy, that pair of positive and negative ion is called Schottky pair of ions. So positive and negative ions missing from their lattice side. Now this is found that this Schottky defect is in those ionic compounds which have found in those ionic compounds which have high or higher coordination number. Very important point to remember. It is found in ionic compound. Second, electrical neutrality is not disturbed. Then higher coordination number, the substances which have, they show Schottky defect. Not only that, those ionic compounds show this defect in which cation and anion, cations and anions have not much difference in their size. Means anions are not too big from cation. So example is your alkali metal halides, NaCl, KCl, KBr, etc. Then in this your Schottky defect, another very important point, density of the crystal density is reduced. Density decreases. Now we'll come to the Frankel defect. The second defect is a Frankel defect. Frankel stoichiometric point atomic defect. So Frankel defect. In Frankel defect, this is also common in ionic compounds, and I draw that again for you. 1, 2, 3. These are constituent particles which are in a crystal holding their orderly arrangement through the bond, which bond is electrostatic in nature. So this is showing lattice, that is a network of the crystal associated with the particles. In this case, you have the positive ion, positive ion, negative, negative, positive, negative, positive. This is your orderly arrangement. When the defect is caused, Frankel, what happens? One of the cation, in this I showed, so there will be many. This cation will leave its lattice site and will cause a cationic vacancy. And from here it will move to nearby interstitial site. The space between the ion is called interstitial site. So here this is your interstitial site. So cation has shifted there. So what do you see here? That is, electrical neutrality is not changed. Number of positive and negative ions are exactly the same. So crystal is electrically neutral. And what else you see here? That is, this is found in those ionic compound, or this is due to what? The compounds which have a low coordination number. Schottky defect, they had higher coordination number, here they have lower. And there you saw the cation and anion, they were not having much difference in this side, in their size. But here anions are much bigger in size than cations. So in this case, alkali metal halides cannot show this Frankel defect, because alkali metal halides, what will happen? Alkali, that is your sodium ion, and if halide I take chloride ion. This alkali metal positive ion is quite large, so it will not be able to fit into the interstitial site. You saw that the cation left its place and gone in the interstitial site. It has come over here. So this is so big that it cannot fit into interstitial site. Therefore, this alkali metal halides will not show. So example of this is your silver halides. Okay, they will show silver ion is having very small size, and halides have quite big size. So anions are big, and this is a small. So easily these cations are fitting into this interstitial site. AGPR is an example which will show both the Schottky defect and Frankel defect. It shows both the Schottky as well as Frankel defect. And in this case, the density of the substance of the compound is not affected. It remains the same. Now we will come to second kind of point defect, that is non stoichiometric defect. The meaning is clear to you of non-stoichiometric. That is, non-stoichiometric means what? That because of the defect, the stoichiometry of the substance will be disturbed. The formula ratio of the constituent particle will be disturbed. And these compounds are also called Bartholide compounds. And in this, electrical neutrality is balanced, maintained by attaining an electron or maybe electrons, or by attaining a positive ion. So this is your about this, and this is due to the presence of an extra positive ion, metallic ion, or the presence of an extra negative ion, that is non-metallic ion. Now we'll do the kind of this non-stoichiometric defect. So first is metal axis defect due to anionic vacancy. Now here again I draw this 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and this is a lattice side, the network of the lattice. Okay, so positive ion, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. In this case, one of the anion is missing from its lattice side and causing anionic vacancy. Because of this anionic vacancy, one electron occupies, this anionic vacancy. From where it comes, I will tell you later. And so this first is what anionic vacancy is caused, and that is occupied, or an electron is trapped in this vacancy. So electrical neutrality is maintained. Electrical neutrality is maintained. How does I tell you? When these crystals, this compound, an ionic compound, this is brought in contact of alkali metal vapors. This crystal is brought in contact of alkali metals, then this vacancy is caused. And when this vacancy is caused, the anion which is out from here, it comes on the surface of the crystal. And the surface, when it comes, this anion at the surface of crystal, it comes in the contact of alkali atom, which is here surrounding the vapors. So alkali metal atom combines with this, and metal atom, when combines with it, the metal atom which is neutral, it will come to the anionic form, in ionic form, and will lose electrons in alkali metal. So one electron it will lose, and it will have positive charge. And so this will combine with anion, and the substance will be formed. This electron which is released on the surface is diffused in the crystal and is traveling and is trapped in this vacancy, and thus electrical neutrality is maintained. So this defect is found in those ionic compounds which have a Schottky defect. Okay, and so one thing more I will tell. This anionic vacancy which we had, this is I am showing anionic vacancy which I showed in that particularly. I am taking this part from the crystal which is trapped by electron. So this is called F center. Very, very important. The anionic vacancy is there. How it is caused? When an anion is missing. So anion is less than the number of cations. So cations are more, so it is metal axis. And so this anionic vacancy which is trapped by electron is called F center. F is for Farbe. Farbe means color. This is a German word. It means color. So which is having an electron, and when temperature is increased, that is when it comes in the contact of light, it absorbs when light, then this electron moves from its ground state to the excited state. So when it is moving from ground state to the excited state after absorbing the light, it says to exhibit transition. You know about transition in 11th standard you have studied. So because of this transition, it shows color, and therefore these substances show color. Example, you have to remember potassium chloride is violet in color and lithium chloride is pink in color due to F center. Now the second kind of non-stoichiometric defect is metal axis defect due to interstitial ion, and this ion is positive cation. So in this case you have again lattice points, constituent particle as latticite bonded together through ionic bond, because this is common in ionic compound. So we have plus minus plus minus plus minus plus minus plus minus plus minus. So in this case what will happen? An extra cation will be there. So this is extra cation in interstitial site. To maintain this, an electron will also be trapped here, and so electrical neutrality is maintained. This kind of defect is common in Frankel, the compounds which have Frankel defect. So here this is your second kind of non-stoichiometric defect. Now the third kind of non-stoichiometric defect is a metal deficiency defect due to cation vacancy. Metal deficiency, before this to metal axis. So how it will be? I explain this to you. Let me draw this figure quickly for you. This is what? The bonds forming the lattice, and constituent particles are held in their fixed position. So plus minus plus minus plus minus minus plus plus minus minus plus. In this case, one of the cation will be missing. Okay. Then from the nearby, now this is what is the feature of this, although it is in ionic, but it is shown by those metallic ions or those metal compounds which have variable valency. Remember that, variable valency, like copper, cuprous, cupric, variable valency, iron, ferrous, ferric, lead, plumbous, plumbic. So this means transition metals they show variable valency. So in this case one cation will be missing, and from the nearby the cation which is here, that will go in its higher oxidation state. If here this is a vacancy, this is cationic vacancy. This is cationic vacancy. Cationic vacancy, and here this is metal ion in higher oxidation state. If here it is your copper Cu plus, then here it will be Cu plus 2. So this is what how the neutrality is maintained. And so this is all about your defect, non-stoichiometric. Now third kind of defect is there, that is defect due to impurity, and that we will do in the next class. So till then, bye. Have a nice day.